Welcome back to our third installment of our series, our third installment of our videos, sequence of videos on sequences, funny enough. Our third installment of videos on 9.1 sequences. So we're going to wrap up this section. Takes a little bit of time. There's a lot of legwork that we have to do at the beginning because everything else we do in chapter 9 is kind of hinged upon our understanding of sequences and the things that we can do with them. And so we're going to wrap up this by just looking at a couple properties that sequences can have. Right now, it may not seem as interesting that sequences can have these properties, that they possibly could satisfy these two things, but later on it might be important to know. And so we're going to look at two properties, specifically what we call monotonic and then bounded. And then we're going to put them together in a very special way. And so first, let's just get the definition out. The first definition we're going to look at is what it means for a sequence to be what we call monotonic. We have two types of monotonicity. We have monotonic non-increasing and monotonic non-decreasing. It's a formal language we use. We're going to see why we say non-increasing instead of decreasing, or non-decreasing instead of increasing. If you just think for a second in terms of math, if I say something's not positive, it doesn't necessarily mean it's negative, because that would include zero. Zero is not negative, but it's not positive. And so in the same way, it's very careful how we're using this terminology. So when we say a sub n is monotonic non-increasing, I mean a sub 1 is bigger or equal to a sub 2. And a sub 2 is bigger or equal to a sub 3, dot, 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 dot. And in general, a sub n is bigger than or equal to a sub n plus 1. And so we think of this and we look at it and we're like, oh, the sequence is getting smaller. Well, not necessarily because of the or equal signs. It actually could be constant. It just needs to not be getting any bigger. And so yes, we can think of it as, yes, the sequence is getting smaller or staying the same. So smaller or staying the same, non-increasing. The flip side of that would be monotonic non-decreasing. So now a sub 1 is less than or equal to a sub 2, less than or equal to a sub 3, less than or equal to dot, dot, dot. In general, less than or equal to a sub n is less than or equal to a sub n plus 1. The next term is larger or equal to the previous term. So the sequence is getting larger or staying the same, so it's not getting any smaller. So a property of a sequence could be it's monotonic, non-increasing, or monotonic, non-decreasing. I mean, there's plenty of sequences that have this property. I'll look at a very simple one. Monotonic, a sub n equals negative n. If I look at the terms of this sequence, a1 is negative 1, a2 negative 2, a3 negative 3, dot, 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 dot. I write out the terms of this sequence, negative 1, negative 2, negative 3, negative 4, and they all follow a certain inequality. We have what? Negative 1, well, that's larger or equal to negative 2, larger or equal to negative 3, larger or equal to negative 4. And so it's not getting any larger, it's decreasing, right? Don't be thrown by the larger number. Remember, they're negative, so we're actually getting smaller. More and more negative, so we're getting a smaller and smaller number. And so this guy is monotonic, non-increasing, so it's monotonic. In this case, non-increasing. It's not getting any bigger. In fact, it is specifically getting smaller. So there's plenty of sequences that have this. Well, what about another one? Maybe a sub n is 1 over n. Well, a1 is 1, a2 is 1/2, a3 is 1/3, dot, 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 dot. Write out these terms, 1, 1/2, 1/3. We'd like to say that this sequence looks like getting smaller, right? That 1 is certainly larger than or equal to 1/2, certainly bigger than or equal to 1/3, is going to be bigger than or equal to 1/4, dot, dot, dot. And so we would say that this guy is monotonic, again, non-increasing. How do I prove this formally without just looking at the first couple terms, though, right? I mean, I have my intuition, and in both of these cases, your intuition is correct because it's a very clear thing that's going on. But what if I have a sub n is n over n plus 1? Is this sequence monotonic? Monotonic. Well, mean, we could write out the first couple terms. So a sub 1 is 1 over 2, so 1/2. A sub 2 is 2 over 3. So that's larger, right? So 2/3 is larger than 1/2. So right now we have A2 is larger than A1. So if this was monotonic, so if monotonic, it would have to be getting larger, so non-decreasing, right? Monotonic, non-decreasing. How do I know it is? I mean, I could write out more and more terms and see, maybe get a calculator out, because the next term would be 3/4, which yes, 3/4 is larger than 2/3. And then 4/5, which is, yes, a little bit larger than 3/4. So it looks like it's monotonic, non-decreasing. How would I prove this formally? Well, I would need to understand, hey, in general, is A sub n less than or equal to A sub n plus 1? Why am I using this one? Well, because I looked at the first two terms, right? It's of course, if we were going to be monotonic, it would have to follow whatever the first two terms do. Since A2 is bigger than A1, then I would like to continue that in order to be monotonic. And in that case, that fits here. And so in general, we're looking to see if A sub n is less than or equal to A sub n plus 1. This is our question. Well, let's see in general what that would look like. That would be n over n plus 1. Is that less than or equal to the next term? Well, what would the n plus 1 term be? That would be n plus 1 over n plus 1 plus 1. Remember, it's just like a function, right? You're replacing n with n plus 1. And so in this function, I replace n with n plus 1. I replace n with n plus 1. Giving me here is n over n plus 1 less than or equal to n plus 1 over n plus 2. That's our question. Is this true? If this is true in general for all n, then yes, we will be monotonic and non-decreasing, but I don't know this. And so now we're going to play a game with inequalities and see if we can justify why this inequality is true, if it is. If we run into an issue, maybe it's not always true. We don't know yet. Let's see. N over n plus 1 less than or equal to n plus 1 over n plus 2. Is this true in general? I don't like fractions, so I'm going to cross multiply. N times n plus 2, n plus 1, times n plus 1, so n plus 1 squared. And normally when we multiply both sides of an inequality, we would have to be careful to make sure it doesn't switch directions. But remember, these are sequences. Sequences have domains of the natural numbers, which are all positive. And if I multiply both sides by n plus 1, that's multiplying by a positive. Multiplying both sides by n plus 2, still multiplying by a positive. And so it won't switch the direction of the inequality. All right, well, let's distribute this side. We get n squared plus 2n. Distribute this side, we get n squared plus, FOIL it out, don't be careful, 2n plus 1. Well, wait a minute. We need to know if this is true, right? This is a question. Look at that. On both sides, we have n squared plus 2n. And on this side, we have plus 1. So in fact, this side of the inequality is always 1 larger than this side. And so is this statement true? Yes, this is true. We are happy, and we have shown in general that a sub n is indeed less than or equal to a sub n plus 1. And so we are monotonic, non-decreasing. It is monotonic. This is one way in which we can show something is monotonic in general. I just try to show this inequality or this one. How do you again know which one to choose? Of course, just write out the first two terms, right? Whatever happens in the first two terms would then have to happen in general. And since I saw that A2 was larger than A1, then I would like to continue that. So that means I would want to show this one. If A2 was for some reason smaller than A1, then we would like to show this one. And what we could do is then in general, try to show if this statement's true. Write out the nth term, write out what the n plus 1 term would be, and try to reason through this inequality. If you can reason through why it would be true. In this case, we can. Why? Because, well, here, these are identical. All right, same thing on both sides. The only difference is this side has a plus 1. So is this true? Yes, of course this is true. This is 1 larger than the other side. Always, for all n. And so this is true in general. If we ran into an issue at any point and we weren't sure that this was true or it wasn't true in general, then we wouldn't be monotonic. And that's okay, right? Sequences don't have to be monotonic. This is just a special property that a sequence can have. And so one way to show monotonicity is just showing it by brute force, right? Proving these inequalities. Showing that either a sub n is less than or equal to a sub n plus 1, or that a sub n is bigger than or equal to a sub n plus 1. Writing out those terms and figuring it out. The other way would be taking this maybe, and instead of going this route, just writing out the terms and the sequences and figuring out if it's monotonic, would be instead to employ calculus. What do I mean by that? I mean, hey, well, I can write this function on 1 to infinity, and on 1 to infinity, there's no issue with this function. Sure, it's discontinuous at -1, but I don't care. We're only looking at sequences. Sequences start at 1, so we're fine. On 1 to infinity, there's no issues with this function. It's continuous. It agrees with the outputs of the sequence. And so if this function is monotonic, then this sequence would be monotonic. Now, what would it mean for a function to be monotonic? Well, right, so one output's always bigger than or smaller than the next output, so either we want it to be going down or constant or going up or constant. If you think back to Calc 1, we would like to then say that this function is either decreasing or increasing always. What do we mean by decreasing or increasing? That has to do with the derivative. If the derivative is positive, the slope is positive and the function's increasing. Remember Calculus 1 talked about determining when a function is increasing or decreasing, and that uses the derivative. If the derivative is negative, that means the function is decreasing. And so how can we use calculus? We can use derivatives here. Remember, a sub 1 was 1/2, and a sub 2 was 2/3, so we still need to have an idea of what we're trying to show. In this case, we see a1 is less than or equal to a2, and so if it was monotonic, we would want to show non-decreasing. What does that mean for us? We would like to show f prime of x, the derivative, is always bigger than or equal to 0. Why? If the function's derivative is bigger than or equal to 0, then that means the slope is always positive or flat, and therefore the function's not getting any smaller. It is non-decreasing. It's either increasing or flat, positive slope or 0 slope. We don't need to necessarily show this everywhere. I'll add the addendum on 1 to infinity. We just need to make sure that for x values from 1 on, that the derivative is positive or 0, since this function has other outputs. And so let's take the derivative of this function. Oh, okay, well, it's not L'Hopital's rule, right? Derivative, now we need the quotient rule. So the bottom function times the derivative of the top minus the top times the derivative of the bottom, all over the bottom function squared. And so what do we get? We get x plus 1 minus x over x plus 1 squared. That's the derivative. The x's cancel in the numerator, leaving me with 1 over x plus 1 squared. Funny enough, actually, if you think about this derivative now, f prime of x is 1 over x plus 1 squared. No matter what you plug in for x, actually, we don't even care that it's 1 to infinity, any value of x would give me a positive derivative. Why? Because I've squared the bottom, and squaring makes things positive. 1 over a positive number is still positive. And so actually the slope is always positive. I mean, the slope doesn't exist at -1. The function's not differentiable at -1, but that's okay. We only care from 1 on. And from 1 on, yes, this is always bigger than or equal to 0 on 1 to infinity. In fact, it's actually always bigger than 0. It actually never even equals 0. But that's all we need. We just need bigger or equal. And so what does that mean? That means the function is monotonic. So another thing we can do besides the brute force way, right, showing these inequalities in general, trying to justify them, is we can actually use calculus in some cases. Not all cases, right? We have to have some sort of function that we can model by a continuous function. And as long as it's a continuous function where you can take a derivative, then you could possibly show it's monotonic that way as well. And so monotonicity is a property that a sequence can have. You can show it either directly with inequalities or with derivatives in calculus. And that's one property. Another property that we're going to look at now is what we call bounded. So given a sequence A sub n, we say A sub n is bounded above, right? Think of what bounded means. It's like under control. So bounded above, we would say, hey, there's some sort of ceiling to the terms of the sequence. There's some sort of value where the terms never go above this value. In fact, there exists a real number m so that the outputs of this sequence are always less than or equal to m. They never go above this ceiling. It's bounded above. Likewise, bounded below. We say it's bounded below if there is some real number k, say, so that no matter where I am, the outputs of this sequence never go below the floor. They're always bigger than or equal to k. There's some sort of floor to my sequence. We would then combine them and say A sub n is bounded if it satisfies both bounded above and bounded below. So if there's a floor and a ceiling to my sequence, we are bounded. And so let's look at a nice example of a sequence that's bounded above. Let's look at 1 over n. 1 over n is monotonic. It is monotonic, non-increasing. It's not getting any larger. In fact, it is specifically decreasing, right? If you look at the terms of the sequence, 1, 1/2, 1/3. And you can show this either with calculus or directly with inequalities. It's not hard to show. It's monotonic. And actually what that means, since it's monotonic, non-decreasing, think about that. That means A sub 1 is bigger than or equal to A sub 2, is bigger than or equal to A sub 3, ... You automatically would then get a bound. Every term then is smaller than the first term, right? A1 is bigger than A2, A2 is bigger than A3, so A1 is bigger than A3, A1 is bigger than A4, then bigger than A5, and so we automatically get a ceiling. Since this sequence is monotonic, non-increasing, it is automatically bounded above by A1. What that means in reverse, or in the other side, is, hey, if you're monotonic non-decreasing, then you're automatically bounded below. For example, if we look at that sequence we just did on the other board, n over n plus 1, remember that this one was monotonic non-decreasing. What did we see? We saw A sub 1 was less than or equal to A sub 2, less than or equal to A sub 3, ... Well, if we think about what that means, A2 is bigger than A1, A3 is bigger than A2, which is bigger than A1, so A3 is bigger than A1, A4 is then bigger than A1, A5 is bigger than A1. In fact, everything's bigger than A1, and so there is automatically a floor. We get bounded below by A1. So this sequence is bounded below by A1. And this sequence is bounded above by A1. Bounded above and below. That's just because of being monotonic. Now, bounded above and below doesn't mean you're bounded, right? You have to have bound on both sides. Right here, we are bounded above. We have 1 by A1. We are also bounded below, just by inspection, by, well, if we think about this, look at the terms of this sequence. It's 1 over n, and if n goes off to infinity, it's certainly never negative, right? It's 1 over something. 1 over a positive number. It's always positive, so it's never anything negative. Specifically, it's bounded below also by 0. It's getting smaller, but it never actually gets to 0. It's always positive. So we could say it's bounded below by 0. So actually, A sub n is bounded, this sequence. It has both. You don't always get both. This one has both. It's bounded above and below. In fact, this one is also bounded above by something. It's bounded below by A1 because of its monotonicity. It is then also bounded above, if we just look at it inspecting this function, by 1. Why do I say that? Well, if we look at the outputs here, we get 1 over 2, 2 over 3, 3 over 4, 4 over 5, dot, 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 dot. That's the sequence. The denominator is always 1 larger than the numerator. Bigger denominator, right? It's a number then less than 1, always. 7 over 8, 8 over 9, 100 over 101. This number is always less than 1, so it's bounded above by 1, just by inspection of our sequence. And so again, an equals n over n plus 1 is also bounded above and below. Well, both of these sequences are monotonic, and they are bounded. Monotonic and bounded. Now, if we put these two properties together, we're going to get something about the convergence of these sequences. So let's think just intuitively for a second of what both of these properties represent, and we'll just kind of think in our head, visualize it. Monotonic means it's not getting any smaller, so it's either getting larger or flattening, larger or flattening, larger, flat, larger, flat. Monotonic non-increasing, so it's getting smaller or flat, smaller or flat, smaller or flat. Both of these sequences will have a ceiling and a floor. So imagine the room that I'm in, or even this whiteboard, right? The top of the whiteboard is my ceiling, the bottom of the whiteboard is my floor, so who cares where I start? Somewhere here, bounded between these two numbers. My sequence is stuck in this whiteboard. So I have like a marker here. And I start drawing my marker, and say it's monotonic non-increasing. So it's not getting any bigger. So as I draw it, my finger, as I draw this, should either be staying constant or going down. Well, if it's constant or going down, and I continue to do this forever, remember this sequence never ends, it's constant or going down, eventually I'm going to get arbitrarily close to the floor. Arbitrarily close to the bottom of this whiteboard, the marker holder. What does it mean to become arbitrarily close to the marker holder? That means that the limit is going to be the marker holder. Likewise, say I'm bounded here, so I have my ceiling and my floor, and here's my sequence, who cares where I start between them. And say we're monotonic non-decreasing, so I'm not getting any smaller. So as I move my finger through this sequence, I need to either be going up or getting constant, and I'm going to be doing this forever. Eventually, at some point, I'm going to be coming arbitrarily close to the ceiling, the top of the whiteboard. And if I become arbitrarily close to the top of the whiteboard, that means my limit is the top of the whiteboard. It's approaching. It's becoming arbitrarily close to the whiteboard, top of the whiteboard. And so both of these properties together imply something about convergence. In fact, we have a very nice theorem. It doesn't tell you what it converges to, but it does tell you that a bounded monotonic sequence must converge to something, either the floor or the ceiling. A bounded monotonic sequence converges. And so this is a very important term that we're going to use. It's going to become arbitrarily close to something. The term that we're going to use is what we call converges. So it becomes arbitrarily close. And so if we can wrap up with this nice theorem, it tells me that it converges. Now, how is it useful? It's not really useful right now. It's just some important properties to consider and talk about. And this is the type of terminology that we're going to use from now on. So we'll write it down. So we say a sequence A sub n converges to L if the limit as n goes to infinity of A sub n equals L. So converges if we can find a limit, if we were getting arbitrarily close to something. We say a sequence A sub n, the other term we're going to use is what we call diverge. Diverges if the sequence, we'll just say the sequence's limit does not exist. Does not exist does not mean it has to blow up. It could blow up to infinity, or it could just not exist, right? It doesn't approach anything specific. Okay, so we say the sequence diverges if it doesn't approach anything. There is no value that we're approaching. We say it converges if it does approach something. And so we talked about sequences. We talked about what we meant by the limit of a sequence. It's what it's going to. We talked about properties of sequences, and then putting all that together, we're going to talk mainly a lot about what we call convergence and divergence. And so the term we're going to use for, hey, the sequence is going somewhere. It's approaching a specific value, L. What that means is we're going to say the sequence converges to L. It's approaching that number. If we have a sequence and say it doesn't go anywhere, it just blows up to infinity, or it just oscillates between two numbers and never approaches anything specific, we would say that sequence diverges. It does not approach. It's the opposite of converge. It does not approach anything specific. And so these are the two terms that we will use for the remainder of this chapter. We'll see these terms come up again: converge and diverge. Converge and diverge. That's going to be the overarching question to everything that we do. And so with that, we wrap up 9.1. So we have the footwork, the framework for chapter 9, which is sequences. And now what we're going to do is we're going to start working with them a little bit more. We're going to talk about, well, what can we do with sequences? What are some interesting things to talk about? And we're going to talk specifically about series. All right, now we'll begin 9.2.